Hey chemistry peeps, Jess McCartney here. So today we're going to talk about catalysts. So the first thing I want to show you is what's known as elephant's toothpaste. So elephant's toothpaste is a reaction that you may have seen in your chemistry classes or science classes where hydrogen peroxide reacts. Now hydrogen peroxide does react by itself, it decomposes by itself, but it's a very, very slow reaction. So without the addition of a catalyst, you would actually not see anything occur. Now when you do add a catalyst, now this can be yeast or it can be a chemical catalyst such as potassium iodide, you will see this foamy substance occur. Now this is obviously with detergent added into it, and you would see the oxygen being trapped in those bubbles and see this lovely overflowing colourful reaction known as elephant's toothpaste. So we're going to talk about catalysts today. The study design dot points that we are going to cover is the role of catalysts and how it increases the rate of specific reaction. We're going to talk about this in terms of an alternative reaction pathway, in particular lowering the activation energies, and we're going to show how this is represented using energy profile diagrams. So what is a catalyst? A catalyst is a chemical that can be added to a chemical reaction that increases the rate of reaction. Now, how this is done is that it provides an alternative reaction pathway. So it doesn't actually undergo any type of reaction itself. All it does is that it lowers that activation energy so the reaction can proceed at a lower energy than what it originally would have proceeded in. So therefore, it does not get used up in the reaction. It will be left over at the end of the reaction, and therefore that can be collected and reused again and again and again. When a catalyst is in as part of the reaction, a greater proportion of collisions between particles exceed the activation energy barrier. So therefore, the percentage of successful collisions would increase because they need a lower energy to overcome that activation energy. Catalysts only lower the activation energy reaction. It does not change the enthalpy change of the reaction at all, or the amount of products produced. So it only lowers the activation energy of the reaction. Now this image here is showing what happens when a catalyst is supplied. So you can see that you have the nitrogen and hydrogen, and this is the reactants for the reaction, and it's coming onto an ion catalyst surface. Now this surface, the molecules bind with the catalyst and the reactions, and it breaks the bonds of the reactants. Now, this is all done, obviously, all at once. So because of this surface catalyst, this will increase the amount of products that's produced because it increased the efficiency of these bonds broken initially. Now, one thing I want to note is that catalysts can speed up or slow down chemical reactions. There are catalysts that are specifically involved in slowing the rate of reaction. And the reason this might be needed, if you think back to our green chemistry principles, is that sometimes you need real-time analysis for particular reactions to collect any type of pollutants that may be produced in your reaction. So catalysts can be used to slow down a chemical reaction as well as speed up. So catalysts are split up into two categories, and this is depending on the state that they're in compared to the reaction that they are being a part of. So the two types of categories are homogeneous catalysts, and this is when they are in the same state as the reactants and the products of the reaction. So remember that word homo, the prefix means the same. So that's when you can remember that it needs to be in the same state as the reactants and products in the reaction. Then you have the heterogeneous catalysts, and these are when they're in different states to the reactants and the products. So this will depend on what catalyst you're using, and the reaction that it's being a part of will depend on whether it's categorized into homogeneous or heterogeneous. So when we represent reactions, we use what's called an energy profile. Now, we have looked at these before in lesson 1D when we spoke about enthalpy changes. So this is an energy profile diagram. Now, the difference between this one and the ones that we've looked at before is that this shows the alternate pathway that the catalyst does. So you can see here that we have a second dotted line just here, and this shows that when a catalyst is applied to reaction, that it, instead of it undergoing this big activation energy, it supplies a different pathway for the reaction to proceed, and it's much lower in energy. So the reaction is going to proceed at that lower energy rather than the higher energy. And that's essentially what a catalyst does. So when you are representing a catalyst in an energy profile, you are always showing that lower activation energy. Now, you would notice that it does lower the activation energy for the forward reaction, so reactants to products, and also the backwards reaction, so products to reactants. So that's something to take note, especially when we start talking about energy profiles in a few chapters' time. So it lowers the activation energy for both forward and backwards reactions. So to summarize, catalysts provide an alternate pathway for the reaction to proceed. So this lowers the activation energy, and this will be both for the forward and reverse reactions. They are split into two categories: homogeneous catalysts, which are in the same state as the reactants and products, and heterogeneous catalysts, which are in different states to the reactants and products. It can be represented by an energy profile, which is shown here, and all it does is that it shows the alternate pathway lower than the original activation energy, which is this one here. What we're going to be looking at next is Chapter 4, Progress Check. I will see you then. Bye-bye.